seminar series. Today we have with us, it is our privilege to have Dr. Khalid Saifullah with us. Uh, there are many students in the audience to just let you know about Khalid Saifullah. He's a PhD student. He's a PhD graduate from Azam University. But the later on, he got postdoctoral fellowship in important places, and among few notable things, there are many notable things in his career, but probably the most important part to mention is for the student is that he has the privilege to be supervised in his postdoc by the field medalist Chin Yao, and he also collaborated one paper with the field medalist. Dr. Khalid Saifullah has been a star teacher in Qaid-e-Azam University, and his research interests really involve broad mathematical topic. So if it is always pleasure to meet him and talking and discussing about math. He always happened to catch important events in mathematics, particularly I think the last climax before the death of Michael Atiyah was his claim of the proof of Riemann hypothesis in Heidelberg laureate form, and he is among those who were sitting there and listening to Michael Atiyah's claim of his proof. So today, this shows that he has very updated mathematician, and all of the youngsters who are attending this seminar, this is a good habit you should everyone should be following. So now, today, Dr. Khalid Saifullah is going to deliver his first talk in our John Conway Spirited Seminar Series, and we hope that in future he will keep on presenting in our series. So today he will be talking about using these symmetries to solve Einstein field equation. So we welcome Dr. Khalid Saifullah. We welcome everyone in this John Conway Spirited Seminar Series. Over to you, Khalid.
Okay, thank you, Imran Anwar, for the nice words. Uh, Actually, I published two papers with Shintu Yao, and some other work is also is in process with the students. Okay, thank you for inviting me to this series, and I thank the LAM's mathematics department also for giving me this opportunity to say something about one of my favorite areas. Okay, so this actually is about two things, the Lie symmetries and Einstein's equations. And I'm not assuming uh, that the audience today has a background of Riemannian geometry, or they work in Einstein's field equations. So uh, I have included some basic uh, terminologies and definitions and things. Even if some people have a background of these areas, this will be a reminder, uh, and this will serve the purpose of setting my notation today. So I've included. So basically, this serves as a purpose of an introduction to the subject also, the Lie symmetries and their use in mathematical physics. And apart from this introduction, I will include some research issues and even talk about a couple of a couple of open problems also. So I hope I'm audible. Can you hear me? Huh?
Yes, yes,
Okay.
everything is.
Okay.
So I request all the participants to please keep yourself muted during the seminar. Continue, please, Khalid.
Okay. So about three symmetries and field equations, and the background will come from Riemannian geometry and a little bit about the Lie groups that are used here. And by the way of definition, I've included some things that I will. Okay, so these are the most relevant books on this subject. The first one, I will talk about this during my talk also, and I'll refer to as Malcolm McCallum's book. He was the editor of this. This is one of the most cited books on this subject of the solutions of Einstein's field equations. It's the first edition came in 70s, and now this is the second edition. I mean, there were many hundreds and thousands of reprints, but this is the second. The second book is by Graham Hall on this subject, symmetries and curvature structure, and many theorems that I will mention later. They're basically from these first two books. These statements and their proofs are also there in these books. Then the third and fourth, they are very old books by Eisenhardt, and one of the earliest books on the subject of symmetries. And then this fifth one is an application with some background and application to differential equations as well as mathematical physics. Okay. Okay, so this just to set the notation, the manifold I'll represent by M with a metric tensor G. And if I am talking about four coordinates, I will label them as x0, x1, x2, x3 from 0 to 3. Sometimes I will restrict myself to the four dimensions, and some things will be general, more than four dimensions. So, okay, so in Cartesian coordinates, these four will be t, x, y, z. I will denote them by these, and if I am in spherical geometry, I'll denote them by t, r, theta, phi. Equation 2 is the most general Riemannian metric with the summation convention. So throughout this talk, I am assuming summation convention, which means that if an index appears twice in, in a term, in an equation, then the summation will be assumed. So this, for example, in equation 2, there is a summation on the index A and B. So it's general for n-dimensional manifold, or if it's a space-time, then it will be four-dimensional. The signature is plus, minus, 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 and Minkowski space is the ground state space, as you know, is the trivial solution. Is in Cartesian coordinates is of course plus 1, minus 1, minus 1, minus 1 on the diagonal, and in spherical coordinates, you know, is minus. Okay, so if it's the signature is minus, plus, 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 then it's minus 1, plus 1, r square, and r square sine square theta. So for example, equation 3 is the length square in Minkowski space, which is the space of special theory of relativity, the flat space. Here c represents the speed of light. Sometime I will ignore this c. By ignoring means I'll take c equal to 1. But c here is actually to give all the terms the same dimension. So c with multiplied with the time gives the dimension of the length. So all the terms have the dimension of length on this now square of the length in equation 3. Okay, so this is a combination of the partial derivatives of metric tensor, which is termed as Christoffel symbols. This is a connection symbol one in Riemannian geometry. And this comma represents the partial derivative. The G with upper AD represents the inverse of the metric tensor. So this particular combination is Christoffel symbols, and they are symmetric in lower indices. So ABC is equal to ACB. So in terms of Christoffel symbols, the next tensor that I will use is called the Riemann curvature tensor, or the Christoffel Riemann, or just the curvature tensor. It has many names. So equation 6 is its definition. The Riemann curvature tensor, it's rank 4 tensor. The metric tensor was rank 2 symmetric tensor. This is a rank 4 tensor, and its symmetries are given. These are the algebraic symmetries, that is the symmetries of the indices. So for example, in the first pair, it's a skew symmetric. In the second pair also, it's skew symmetric. And it's symmetric if the pairs are interchanged. That is ABCD is equal to CDAB. So it's the same. Another symmetry that it obeys is called Bianchi's identity. So there are two identities. This is Bianchi's first identity, the algebraic identity. Another one is a differential identity. Okay, so this Riemann curvature tensor. In this tensor, if we contract the two indices, for example, A and C, in this definition, A is contracted with C, then the rank will be reduced by 2, and we will get a second rank tensor, which is called the Ricci tensor. So this will also be useful in the later discussion, the Ricci tensor. And if I further contract it or take the trace, so you can say we're taking the trace, or you can say we could contracting it, we will get a Ricci scalar as in equation 8. So this contraction from the definition of the Riemann tensor gives us a new definition of the Ricci tensor also, which is given in 9. This Ricci tensor is also a symmetric tensor. Okay. Another tensor which is important for today's talk also and for the field equations also is the energy momentum, stress energy momentum tensor. So it's also called the energy momentum tensor, and some people just call it as matter tensor also, because it contains all the properties of matter. Unlike the stress strain tensor, the three-dimensional stress strain tensor in elastrodynamics or other fields of Newtonian dynamics, which gave us the properties of the matter, this tensor gave us not only the distribution but motion of matter. So that is the main difference. So the distribution and motion of matter, all the properties of matter, whether it's neutral or charged or the pressure or density, the equation of state, etc. If it's a pressureless or the dust matter or whatever, so everything is contained in its if it is in 4 dimensions, it's in 16 components. All the information, not only about the distribution, but the motion of matter.
Mamala,
So,
Mamala.
so when we say that it contains the information about the motion of the matter also, this means that the energy and momentum, all information is contained. And again, this is also a symmetric tensor. So all these rank 2 tensors so far we have discussed are symmetric. Now, a combination of all these tensors that defined is called the Einstein tensor, GAB, given in equation 13. So just I remind you, the first term is the Ricci tensor minus half, and then this is the metric tensor, and then R is the Ricci scalar. This, because this is a combination of symmetric tensors, so this is also symmetric. And another property which is very useful for the field equation is that it's divergence free. So it's the divergence. If we take the divergence, you know the summation on this derivative on in A is 0. So this divergence free, the property of being divergence free, the Einstein tensor shares with the energy momentum tensor also. And this led Einstein to compare these, to actually write them in proportionality. So I repeat it again. He noticed that the Einstein tensor is also divergence free and the matter tensor is divergence free. And then he wrote them proportional to each other. And this is called Einstein's field equations. So this here 8 pi g over c4 is the constant of proportionality. Capital G is Newton's gravitation constant. Note that here there is an extra term on the left hand side. So there's the third term, which is gamma GAB. So this gamma is called, lambda. This lambda, capital lambda, is called cosmological constant. So I'm just mentioning here for the sake of completeness. Otherwise, in the rest of the discussion, I will ignore this term. This becomes very important when we're talking about cosmological solutions. Otherwise, we usually ignore it. And even if it is there, it's the value is very small. So these are Einstein's field equations, and their significance and importance cannot be overemphasized. No, we use the term a lot that the significance of something cannot be overemphasized. But in my opinion, in mathematics and physics, the use of this phrase that their importance and significance cannot be overemphasized is I think nowhere as appropriate as in the case when we are discussing field equations. These field equations were written in 1915. The first solution came in 1916. So about 108 years after the writing of these field equations, they are still as important as they were originally. People find their solutions. I mean, they're continuously finding their solutions. There are new solutions not only every year, perhaps every month, if not every week. So new solutions coming out from these. If briefly discuss the physical importance of those solutions. So, well, the most important classes are the astrophysical solution and cosmological solutions. Astrophysical solutions mean they represent stars. They represent a distribution of matter. Now, well, mostly, I mean, the original interest was with the spherical symmetry, because people have always maintained that that the objects in this universe are spherically symmetric. So the first solutions naturally then that appeared were spherical solutions. But these spherical solutions with different equations of state, different relationship between density and pressure, different electromagnetic properties like charges, for example, the magnetic charge, the electric charge, and the other charges that exist in physics also, or the neutral bodies. So whatever we can think of, what whatever is dictated by physics or mathematics or just imagination, I mean. So there are many solutions which some people used to think they are not physically important, and they don't have any physical significance. But later on, it was proved that they are very important physically. Then similarly, there's some solutions which people thought they're very important from the physical point of view, from astrophysical point of view, but later it turned out that they're not physical. Then there are some mathematical solutions only, and there's some solutions about which there's still some debate whether we can attribute some physics. I mean, there are thousands of solutions. So the first book that I talked about, uh, it contains thousands of solutions. It's actually a catalog of the solutions of Einstein's field equations. So these are astrophysical solutions, and from physics point of view, the important solutions are cosmological solutions also. That is, those solutions which attempt to explain our universe, the cosmos. And there are different cosmological solutions also on this. So this is the physical part of the significant. Actually, there, as I said, this is so much important that I can easily spend 1 hour just talking about their physical and mathematical significance. But today's talk is more about mathematics. Mathematically, these are actually partial differential equations. So if I, okay, yeah. So this is the solution without the third term, without cosmological constant term. This is the field equation that I will be dealing with in this talk. So mathematically, this is a set of partial differential equations. So if we talk about 4 dimensions, in 4 dimensions, because all the tensors here are symmetric, so in 4 dimensions, these are 10 partial differential equations. And now what is how do we define its solution? So solution is a metric tensor, like the line element in 18. Any metric tensor that satisfies this equation 17 is called its solution. So by satisfying means the right hand side is equal to the left hand side. And this becomes homogeneous if the right hand side is zero. If there is no matter, the vacuum solution, so-called vacuum solution of 17, will give us the homogeneous uh, partial difference, set of homogeneous partial differential equations. Now, how to solve these equations? Now, this is famously known as, these equations are a marriage between physics and mathematics. So people say the right hand side is the physics and left hand side is mathematics or geometry or imagination. Or what John Wheeler used to say, that these equations emphasize that the geometry tells matter how to move, and matter in turn tells geometry how, tells the space how to curve. So it's a combination between curvature and matter, matter on the right hand side and curvature on the left hand side. People have written a lot about the philosophical significance and meaning of these equations also, but of course there's no time for us to go into that. So keeping myself to the mathematics of these equations, so they're all the methods that are used to solve partial differential equations that have been applied to these set of equations. They've used all the methods that were available. Apart from that, there are new methods developed in mathematics, just motivated by the solution of these. So in an attempt to find the solutions of these equations, many new methods. So these equations led to a development in mathematics also. So a lot of techniques people developed for solving these equations. And particularly in numerically, when we solve numerically, there are many people who think that now to find a new solution analytically is very difficult, not if not impossible. So most of the people now are attempt to find the solutions by using numerical techniques. So many new numerical techniques have been developed just to solve these equations. New packages, new softwares, new add-on packages for the existing softwares, they have been developed just to find these solutions, to have um, the physical interpretation and simulations. So for example, Einstein toolkit is one of the very important package that has been developed for solving these equations. Then there's another package which is very common, is black hole perturbation toolkit. These are some of the more famous ones, but there are many other uh, packages, softwares that are available for finding the solutions. But today I will restrict myself only to one technique, and that is the symmetry method for solving these equations. And I will now, okay, so just I'll mention two or three important solutions. For example, the Schwarzschild solution is, this was the first solution that appeared in 1916. So it is called the Schwarzschild solution. Also, it's now become clear that Schwarzschild was not the first person, not the only person who gave the solution, and he was a very senior astrophysicist, German astrophysicist in 1916. But at the same time, there was another guy, poor guy by the name of Droste, who was doing PhD. And I think the title of his thesis was on Einstein's field equation. And he also presented this solution in his PhD thesis at the same time. But and now it has been established historically, but all the books call it as the Schwarzschild solution. So we can go by that name. So here you see that m is the mass of the source. So any object, whether it's a star or planet or any matter in spherical symmetry. So the whose mass is represented by this m. So note that in the second term, If r is equal to 2m, then there is a serious problem. And serious problem means that there is a singularity. The solution becomes singular. So this is called the event horizon. So GRR, the second metric coefficient, if we take its inverse and put equal to 0, this gives us the position of the event horizon. So this is the event horizon. So I'm in this physically very important surface where this and a lot of peculiar things happen on this surface which do not obey the laws of physics. And even Einstein, I mean, refused to accept this solution, and because he said that here the particles will be moving very close to the speed of light, so and the laws of physics will break down and so on and so forth. But uh, the later developments, actually the recent developments of last 10 to 12 years have shown that these things actually exist in this universe, and this solution is a physical solution. The next solution is called the Rison-Armstrong solution. And then if we compare this with the first solution, you notice that there is an extra term represented by q square over r square. Here Q is represents the charge. So if a matter or a star is charged, then equation 20 will be the solution of that. And if charge becomes 0, of course, it will reduce to 19. Okay. Another important solution is the Kerr metric. This contains rotation also. Notice that now it has become more complicated than the previous one. So J represents the angular momentum, the spin of the body, the star or whatever spherical object we have at our hand. Okay, so and it's the singularity. Now there are two singularities, as in the previous case. Also, you've noticed in 20 also, because if we put the second term equal to 0, now this will be a quadratic solution, and it will have two. This will be a quadratic equation. It will have two solutions, r plus and r minus. These are called outer horizon and inner horizon and so on. Well, I will not go into these details. Similarly, here also, this will give us a quadratic equation, and we will have two singularities, and its nature is different from the previous one, but again, I will. And this is in some sense, the most general of all these solutions, which contains the angular momentum and the charge and the mass. So all three parameters. So we say that this is a 3-parameter solution with mass, charge, and spin. And of course, if we put charge or spin equal to 0, it will reduce to the original one. So just to mention some solutions, I will now go on to the subject of Lie symmetries. So somebody wrote in a book on Lie symmetries that Lie derivative actually lies at the heart of the subject of Lie symmetries. So just to remind you about the definition of the Lie derivative and how we get a Lie bracket from this actually, which will be used later on. So 28 is just the dragging of a function mapping ht from a point 0 to another nearby point to its neighborhood point from ht0 to htp. And this is the usual definition of differentiation on the right hand side. But so this, in some sense, this is a generalization of the directional derivative. And here the direction is given by the vector v. So we call this as so T is the tensor. So we say that this is the Lie derivative of tensor with respect to the vector V. Some people call it relative to V or along V. So the different ways of expressing it. But another important thing to note is that if T is of type Rs or valence Rs, then its Lie derivative will again be a tensor of the same valence. So whatever is the valence of the tensor T and the rank of tensor T, that will be preserved under this Lie derivative, and then this will give rise to another tensor. So if in coordinate basis, if we write this in coordinate basis expressed by dx and dy, this will become the 29, you can see, like an operator. So this is an operator because ht along with this vector u is this uh, 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 chain rule, using the chain rule, and it will become more clear on the next slide, for example here. So if we in place of tensor I take a vector u, so now we have on the left hand side a vector u, the Lie derivative of vector u in the direction of vector v. And just notice this, right? The first term is something like vector v acting on a vector u minus the vector u acting on a vector v. And this fact is represented by what we call as the Lie bracket on the right hand side. So v acting on u minus u acting on v. So this is a commutator bracket also, and it's I mean in mathematical physics it's used everywhere. It's very important there in mathematics also, other branches. But this forms this operation of Lie bracket actually forms the basis of this definition by which we define the Lie algebra. So with this Lie bracket, if we give three properties to this Lie bracket, first is the bilinearity. The A bracket A gives this bilinearity, and it's anti-symmetric. Of course, by definition, from 31 you can see that it's anti-symmetric. V applied on U, and if we reverse it, there will be a negative sign over there. And the Jacobi identity, if we have three vectors U, V, and W, so it's equation 33. So the Lie bracket together with these three properties defines the Lie algebra, and this will be used later, the Lie algebra of our symmetries. Okay, so for example, if we have now two operators, so two vectors, previously I said two vectors, now we have two operators xi and xj, and under this operation of Lie bracket, they will give rise to this operator, another operator you can see, and this quantity in bracket. Note that this is just a number, a constant, and these constant we call them as structure constants. So this means that this Lie bracket on the left hand side will give us will give rise to another new operator here denoted by xj multiplied with a constant, a structure constant. So xk, for example, xk and xl, when there is a Lie bracket on them, we'll get xj, a new vector or generator or operator. So we will use different expressions. We'll call them as vector or generators or operators. So you will see they will be used interchangeably, and there will be a constant here, and this will define. This will give us the definition of the closure of the Lie algebra also, and and if all these structure constants are zero, if I mean the right hand side of all these Lie brackets is zero, then the Lie algebra is said to be a billion Lie algebra. And these structure constants, this is clear from the definition also from 36, that these structure constants, there is a skew symmetry between them in the lower indices. So for example, xk applied on xkxl is equal to minus of xl as xk, which is clear from the definition of the Lie bracket also. Okay, so these are the things that we will be using now. Now we come to the symmetries in the context of these Riemannian geometry and field equation. The first, this is the general definition of symmetry. For example, if we have any tensor T and we'll take Lie derivative, and if this Lie derivative is zero, we say that this T, tensor T, is invariant under this transformation, or this is conserved. Now we will take different tensors that we have defined earlier instead of this T, and come to our main purpose of solving the field equation. So naturally, the first tensor that we should take here instead of T is the metric tensor. That's the basic tensor of this theory. So in 37, if we take the metric tensor GAB, so this is naturally the first symmetry that comes in this field, and actually this is in classical geometry used to be known as the isometry, and people used to call them as motions also. So in old literature, this x, no, let me say it again. So if the Lie derivative of the metric tensor is zero along x, then x is called an isometry or a motion or a Killing vector. It's called Killing vector because the German mathematician Wilhelm Killing, this equation is named after Wilhelm Killing. And so in any space, whether it's Riemannian manifold or any basic space like Minkowski space or whatever, the metric tensor is the most important tensor. So the first symmetry that enters this field is the symmetry of this metric tensor. Now in component form, this 38 can be written as in 39. So note that this is a partial differential equation which involves the components of the vector x, c, and the components of the metric tensor GAB. So in four-dimensional space, for example, because this metric tensor is a symmetric tensor, this will give us 10 partial differential equations. So these 10 partial differential equations in a four-dimensional space will involve 10 components of the metric tensor and 4 components of the vector x. Okay. So if we are given a metric tensor, which means if the 10 components of the metric tensor are given, then our job is to find the 4 components of the vector x, which will give us the Killing vector of the given space, of the space from where we have taken the metric tensor. Okay, so if it's Euclidean space, the metric tensor is from Euclidean space, then the components of x will give us the isometries. The term isometry means same, and metry means the distance. So the mappings, all those mappings which preserve the distance, all those transformations which preserve distance between the spaces, those transformations are called isometric transformations, or motions, or Killing vectors, or simply isometries. Now these 4 components, let me, okay, so I think this is what, this is just some history of the, for example, Bianchi, I mentioned earlier also, he classified all 3-dimensional Riemannian manifolds according to these So by classification means you find all the Killing vectors for all the possible, for all the metric coefficients in a particular space. So Sophus Lie, who with this this subject is named after the Norwegian mathematician Sophus Lie. He also gave the Killing vector algebra for these spaces, and originally they did this for the 3-dimensional spaces, 3-dimensional Riemannian manifolds, and then there were some some cases missing, which were later done by by Bianchi and other people. And later on, Petrov from Kazan, Russia. He also provided this classification of Riemannian space times admitting these motions. And then this subject went on to the four-dimensional spaces. And for example, this is a four-dimensional spherically symmetric space given in 40. So this is a general metric. As you can see, there are arbitrary functions, but this is a static. By static means the coefficients do not depend on time. So obviously, if they do not depend on time, then the first symmetry that we expect this to have is the time-like symmetry, d by dt, which is here represented by partial t. So note that d by dt will be represented by partial t. So if we construct the Killing equation for this space-time and solve it, the minimal symmetry means that this will be a subset of all the symmetries in a spherically symmetric space. So the minimum dimension that the Lie algebra, so note that these are four generators, and if this space is spanned by these four generators, then the dimension of this Lie algebra is 4. So we say the dimension of the Lie algebra is 4, and in our literature, in this literature, some people call this as four-dimensional Killing vectors. So the correct statement is the Lie algebra for the isometry group on this space is 4, but we sometimes say that it's four-dimensional Killing vectors, and the maximum symmetry this space can have is 10. In some slide I will show you this 10 also. There is another example for this is a cylindrical symmetric space. Again, this is static. So in this space, note that this is generated by three generators, d by dt, d by d theta, and d by dz. So in some sense, this is less restrictive than the previous one. The 47 gives us the plane symmetry, and this plane symmetry is more restrictive than for the cylindrical symmetry. So there is an extra symmetry x3 also. And note that there are three generators, three Killing vectors here. But if it is static, then it will have four Killing vectors. Okay. So this is the difference from the 45 to 47. That 45 is static, and there is a d by dt also time-like Killing vector, which is not showing up over here because it's the way it is written is not static. But if it is static, another important thing actually is that these generators actually define spherical symmetry. Sorry, whatever symmetry is there. So for example, if we say the space is cylindrical symmetry, so one way of saying this is that this space has these three Killing vectors. So when we say that space has these three Killing vectors, this means that this space is static cylindrically symmetric. So this is another point which the students, I should emphasize for the students in the audience, that all these symmetries, spherical symmetry, plane symmetries, and whatever symmetries we use, the real mathematical definition of all these symmetries come from these vectors, these Killing vectors. They actually define a symmetry. From this symmetry, you can see that the plane symmetry in some sense can be written as a, as a special case of cylindrical symmetry. So if the coefficient of dy square and dz square are same here, but if they are different, then it becomes cylindrical symmetry. Okay. Next definition is the Lie symmetry of the Ricci tensor. Okay, so the Ricci tensor is again, this is I mean, mathematically, this equation 50 is not very different from the Killing equation. The only difference is that there were the coefficients of metric tensor. Here we have the coefficients. Here we have the components of the Ricci tensor. Otherwise, mathematically, this is also in a four-dimensional space. These are again 10 equations of a similar form. I should not say the same, because there the equations will involve the coefficients of metric tensor. Here it will involve the components of the Ricci tensor. Otherwise, they're mm, they're same. And again, here the solutions x, the vectors x that we obtained from this system of equations 50, they are called Ricci collineations. Okay, so these are again vectors with for the metric tensor we call them as the killing vectors. For the other tensors we call them as the Ricci collineations. So Ricci collineations, there are some properties of the Ricci collineations. I think I should skip them. Uh, this is minimum symmetry. I've already told you for a cylindrical, for example, these are some important results, propositions for the case of cylindrical symmetry. So d theta, dz. So these actually represent translations in t at z and rotation in theta. So this is r cross SO2 cross r. So two translations and one rotation. Another important thing for the killing vectors and for the symmetries is that the minimum symmetry you can see is 3 and the maximum is 10. The other admitted symmetries are 4, 5, 6, and 7. Now there's about a couple of months, 2 months ago also, I was having this discussion with Graham Hall, who is one of the very good experts in this field. He said 9, okay, is clear. There are theorems which exclude 9-dimensional Lie algebras for these spaces. But the dimension x, why the dimension 8 is included, is excluded, is not clear. There is no proof so far, but no one has ever seen any 8-dimensional algebra in this context. So that is also. Okay, so if we replace the Ricci tensor by another tensor, which is called the matter tensor, that I defined earlier, the stress energy tensor, then this is called matter collineation. Okay, so just replacing Ricci tensor with the matter tensor is a matter collineation. And replacing that with the Riemann tensor is the curvature collineation. Now you see that Riemann tensor is a 4 rank tensor. So this system will be a much more complicated system. It's very complicated. Similarly, Weil collineation is, Weil tensor is again a 4-dimensional, 4 rank 4 tensor. The system is similar to that of the curvature collineations. So with all these, now, just to emphasize that we have taken the right-hand side equal to 0 in the previous definitions, but it's not always, I mean, the case. If it sometimes it's not homogeneous, it's non-homogeneous. For example, here in this case, the right-hand side is again a multiple of the metric tensor. Now this multiple, now this depends on whether this psi over there is a constant or a function. If it's a constant, the general class is called conformal vector fields, but if this is constant, it's called homothetic motions or self-similar. You see that Lie derivative of metric tensor is proportional to the metric tensor itself. So this gives rise to self-similar spaces. The term is obvious from the definition. Okay, so this is what I was saying. These homothetic motions or and give rise to self-similar spaces. This also has importance in the solution of field equations. Now, with the introduction of this constant, previously we said the maximum dimension was 10. Now, with the introduction of this constant, this becomes 11 now. So there is an extra generator that comes out here. So there are other symmetries also, which I know I don't have time to talk about them. But note that on salmon, there is an affine collineation. So affine collineation is actually the Lie derivative of a connection of the Riemannian space, of a Riemannian geometry. If the Lie derivative of the connection symbol is 0, then this collineation is called affine collineation. Okay, so now these are theorems which are important. The affine collineation, the set of affine collineation, the maximum dimension is 20 for a 4-dimensional space. And for an n-dimensional space, the maximum is n into n plus 1. The second theorem, the killing, and these theorems and their proofs are given in the first two books that I mentioned on my first slide. If Km represents the killing algebra, Lie algebra for the killing vectors on a manifold M, and HM is the Lie algebra of homothetic motions of a manifold M. So, and this the homothetic the algebra for the killing vector is always less than or equal to 10. For this, for homothetic motion is always less than or equal to 11. And this is a general statement that the dimension of the algebra for homothetic motion is always less than or equal to that of the killing vectors plus 1. Okay. Okay, so similarly for conformal motions, the maximum dimension is 15 for a 4-dimensional space. But for n-dimensional space, the maximum dimension is n plus 1 into n plus 2 over 2. And if this is not conformally flat, by conformally flat means if a space-time can be written can be transformed to a flat space with the help of a conformal transformation, then it's called conformally flat. That is, the space-time and the flat space-time have a conformal relationship between them. So then the space-time is said to be conformally flat. So if it is conformally flat, then the maximum dimension of the Lie algebra will be 15. And if it's not conformally flat, then the maximum dimension is 7. So you see, there is no possibility of any dimensional algebra between 7 and 15. Okay, and then this is the algebra for the curvature collineations, and the set of killing vectors, homothetic vectors, affine vectors, they're always a subset or subalgebras of the curvature collineation. I mean, roughly you can see that because the curvature tensor is constructed from Christoffel symbols, which and they are constructed from metric tensors. So naturally they should inherit all the symmetries of the killing vectors and affine vectors, affine collineations. So this is a roughly you can see, but the proof of all these theorems are given in the books and they are known. Okay, so the important thing that I've just mentioned is the relationship between these symmetries. For example, the killing vector should be a subset, the killing algebra should be a subset of the Lie algebra of all other symmetries naturally, because they come from the metric tensor. So the killing algebra, for example, this space-time, this is an example of a space-time where I've compared I've given the Ricci tensor and the metric tensor, and we see that the killing algebra is a 4-dimensional, but the Ricci collineation and metric collineation are 6-dimensional. And if we look at the algebras, they are subsets of this. So this is a 6-dimensional Lie algebra here. So these are the 6 generators, and this is closed as we have given here. So this is the Lie bracket, which give rise to some other generator again in the same generating set. So this is set that spans the whole space. Important thing to note here is that the metric tensor is always non-degenerate, which means that the metric tensor, the determinant of metric tensor can never be 0. It is always non-zero. But this is not true for other tensors. The Ricci tensor can be degenerate or non-degenerate. Its determinant can be 0 or non-zero, which gives rise to a very interesting possibility that for other tensors, the Lie algebra can be infinite dimensional also. So it can be finite dimensional as well as infinite dimensional. So both the possibilities are there. So this is a possible relationship between MCs and RCs. And this is one of the open problems that we have seen here. For example, there are different possibilities of RCs and MCs. The red here denote that we don't know about these cases, whether they exist or not. Let me explain in 10 seconds. This says the matter tensor is degenerate and the Ricci tensor is also degenerate. So can we have symmetries here? This is an open question. We don't know whether, I mean, for finite case as well as infinite case, we don't know anything about that. Okay, so skipping, this is an important diagram which comes from 1960s, I think, a paper by Katzan and Levine, and it's quoted everywhere. This is an relationship between all these symmetries. So M here is actually motions, killing vectors. I told you in classical geometry, people used to call killing vectors as motions. So motions and homothetic motions. The motion lies at the heart of all these, and Ricci collineation is the most general of all these. So motions is subset of homothetic motions, which are subset of affine collineation and curvature and so on. And Ricci collineation in some sense is the most general, and motion is the most specific, the particular case. Note that matter collineation is not in this diagram. And this brings me to another open question. We don't know actually where the matter collineation should be in this diagram. What our study shows is this, that this is the killing vector is a subset of Ricci collineations, and of course it's a subset of matter collineations also. The next step that our study has shown in our group is that this is the relationship. There are some Ricci collineations that are matter collineations also, and there's some matter collineations that are Ricci collineations also, and there are some matter collineations which are not Ricci. So there are all the possibilities. And killing vectors always lie at the heart of both. But what is the position of matter collineation actually in that diagram is still not understood. Okay, so skipping some of these details, we have developed an algorithm also for finding these symmetries. The algorithm means that this is a general equation. This is, I've called this as killing type equation, but A is not a metric tensor, A is any tensor. So we take any tensor of rank 2, symmetric tensor of rank 2, and solve this set of equations generally. So if we solve this set of equations generally, and we have done this is the 10 equations that, and if we solve these generally, this is the solution. I don't expect you to understand what I have written over there, but just to give you an idea that if we solve this set generally for any rank 2 tensor, then this table will give us all the information about killing vectors, Ricci collineations, matter collineation, any tensor of that space for a tensor of rank 2. So the last column gave us the dimension of the Lie algebra. And we have list of all these generators also given in this algorithm. So in some sense, this this uh, this works as an algorithm for any two-dimensional tensor for finding the symmetries of any two dimensions. There are particular examples also, and I think I don't have this an example. For example, this is a plane symmetric tensor whose Ricci tensor and matter tensor are given here. And from that table, we can easily see that the dimension of the killing algebra here is 4. That for Ricci collineation is 6, and matter collineation is also 6. And there are some more examples also. This is for cylindrical symmetry. Okay, so this is a kind of an algorithm, a flow chart, how this actually works, and how people have, by using these methods, people in our group in Pakistan and in all over the world, they have found new solutions. So what actually happens is that we write the collineation equation or a killing equation. Okay, we solve this system. When we solve this system, we get the components of the vector, which I've written as RCs, plus some constraints, differential equations involving the components of the Ricci tensor. When we solve these constraints, we get the components of the Ricci tensor. Now, getting components Ricci tensor actually gives us the Einstein field equations. And when we insert these components, the field equations, we get the right-hand side, which gives us the energy momentum tensor. And this is what we call as a space-time or a metric. So this is the flow chart of what I have described earlier, that using these symmetries, we in our group and people in other parts of the world, they have found new solutions, and we have also found many new solutions using these symmetries. For example, these are some of the solutions, and I think, talk about one solution, and this is a Kastner type solution. These Kastner conditions in 96 and 97, they describe the Kastner conditions. Sorry. Yes. So together with 91, note that the powers here are 2a, 2b, and 2c. It's a kind of a cylindrical symmetric space-time where written in rho t rho theta z coordinates. Okay, so these powers 2a, 2b, 2c, if they satisfy certain conditions, then the space-time is called Kastner space-time, and this is the condition that they satisfy. Okay, so now for this condition, we have found a solution. This solution, which is a flat metric and gives these symmetries. And if we, instead of A, B, C, we choose these numbers where m is a number here, then we get a new solution. And we can, okay, if we get these solutions, then we can see what are their physical properties, whether they are physical or unphysical, or they're only mathematical constructs, and so on and so forth. So just to summarize what I have said earlier, that metric tensor is the basic symmetry of any space, any manifold actually. uh, and we when we solve the killing equation, this gives us a set of generators or vectors, which give us a Lie algebra. And a four-dimensional space, the minimal symmetry is 4 for a static spherical symmetry is 4, and maximum symmetry is 10. For n-dimensional manifold, the maximum will be n into n plus 1 over 2. And the other symmetries, the other tensors, Ricci tensor, matter tensor, curvature tensor, also give rise to similar equation as the Killing equation, and they also give rise to their particular algebras. And then there are theorems which govern these dimensions of these algebras and their inclusion relationships. Which symmetry is included in the other symmetry? Obviously, Killing symmetry is included on all other symmetries, and the diagram shows the Ricci collineation is perhaps the most general symmetry, and there should be a place for the matter collineation, that diagram also, which we don't have. And there are some cases where we don't have solutions so far that I mentioned. So that's all, and thank you very much for you.
Thank you, Khalid. Thank you very much. There are few questions